There are places in the solar system that seem dead at first glance. Ice balls, craters, stagnation, and then there's Io, a moon that orbits closer to Jupiter than our moon does to Earth, about 350,000 kilometers above the clouds of this gas giant. And this moon is anything but dead. Io is the most violent place in the entire solar system, except for the Sun, of course. Not Mars, not Venus, and not some exotic exoplanet either. A moon. Of all things, a moon. When you see pictures of Io, your first thought is Photoshop, yellow, green, red, black. A surface that looks like a chemistry lab that exploded. And the fascinating thing is, these colors aren't a trick, that's geology. Or iology, but not geology as we know it. My name is Serwan and this is Mars Chronicles. Before we get to Io, we need to take a quick step back. Jupiter now has almost 100 officially confirmed moons. Most of them are just chunks of rock, but 4 of them are different. Europa, Ganymede, Callisto, and Io. The so-called Galilean moons, discovered in 1610 by Galileo Galilei with a telescope that seems almost ridiculous compared to today's instruments. And yet, it was precisely this observation that totally changed our view of the world. Suddenly, it was clear that not everything revolves around the Earth. Today, more than 400 years later, we know that these 4 moons are entire worlds. Ganymede, the largest moon in the solar system, Callisto, ancient, heavily cratered and almost geologically dead, and Europa, an ice world with a global ocean beneath it, possibly hospitable to life. We will know more when the Europa Clipper mission takes place in 2030. Then there's Io. No ocean, no ice, and no water. Io is drier than Mercury and at the same time the most volcanically active body in the entire solar system. Io has around 400 active volcanoes, not has, constantly, and that's not a rough estimate. That's the result of decades of observation, starting with Voyager 1 in 1979. Back then, from 20,000 kilometers away, they saw several active eruptions. And since we're talking about Voyager, we found this model on printables and started printing the Voyager probe here in the studio. With our Core 1 from Prusa, of course. And I have to say, these old probes look completely different as a model. Those delicate booms, the large high-gain antenna that was high-tech in 1977. And this exact thing showed us, for the first time in 1979, that Io isn't a dead chunk of rock, but a geological state of emergency. If you do your own printing or want to start, my Prusa affiliate link is down in the description or through this QR code here. So, and now back to Io, with cameras that were Stone Age by today's standards. And still, you could see something shooting out from the surface. Not lava fountains like in Hawaii, but gigantic eruptions that rise dozens of kilometers high, and sulfur gas fountains that shoot hundreds of kilometers out into space. Io is not a volcano planet. Io is a planetary high-pressure cooker. Where does all this energy come from? Now comes the crucial point. Jupiter is far away from the Sun, about 5 times farther than Earth. It's cold out there. On Io, temperatures outside the lava fields drop to minus 130 degrees Celsius. Where does this energy come from? The answer is brutal, good old gravity. Io is in an extreme situation. On one hand, there's Jupiter with its gigantic mass. On the other hand, Europa, Ganymede, and Callisto also pull on Io. The result is not a stable circular orbit. Io is forced into an elliptical orbit, sometimes closer to Jupiter, sometimes farther away, about every 2 days. And each time, the moon is stretched and released again, and stretched and released again. We know tides from Earth. The moon raises our oceans by maybe half a meter. Io is deformed by up to 100 meters. Not water, solid rock, hot. 100 meters every 2 days. This is not a gentle process. This is constant kneading. This phenomenon is called tidal heating. It's basically mechanical energy that's directly converted into heat. Friction inside, constant deformation. And this energy is enough to massively heat up the interior of Io. Not evenly like a magma ocean, but in localized pockets. Hundreds of small individual volcanic engines working beneath the surface, each with its own pressure, its own dynamics, its own chemistry. And this is where it gets interesting. You have no plate tectonics, no subduction zones, no classic volcanic cones like on Earth. Lava emerges through the cracks caused by constant movement. After a massive eruption, the surface collapses, gigantic lava lakes form. The largest is called Loki Patera and has a diameter of about 200 kilometers, a bubbling active lava surface. For comparison, that's larger than some German federal states. And then there's a second dimension to this. Jupiter has one of the strongest magnetic fields in the solar system. Io is constantly moving through this radiation field. That means electrically charged particles interact with the sulfur gases. The result? Yellow sulfur crystals, white sulfur dioxide fields, green sulfur monoxide zones, and red hotspots with fresh lava. This is not an artistic effect, but physics. Now comes the point that's often missing in standard documentaries. Io is not just spectacular. Io is a laboratory, an extreme case, a place where we learn how gravity generates energy. And that's not just an academic detail. Tidal heating is probably the reason why Europa has liquid water, why Enceladus has geysers, why exomoons could potentially be warm enough, even far away from a star. Io is the most brutal example of what gravity can do. That's exactly why it's so scientifically valuable. Now I'm fantasizing a little, but imagine we find out that there are millions of such moons out there, where life develops inside the moon, not on its surface like we know it here on Earth. Could life or even civilizations really emerge like that? I don't know, and I hope that future missions will bring answers to these questions. But what do you think about my bold theory? Well, that's only half the story, because Juno discovered something that's even more absurd. Massive, isolated, steeply rising mountains. Without mountain ranges, without tectonic plates, single, gigantic peaks that reach 18 kilometers high, twice as high as Mount Everest, on a moon without plate tectonics. How is that possible? So we have a moon that's constantly being kneaded, 400 active volcanoes, lava lakes up to 200 kilometers in diameter, and a surface that completely renews itself every few million years. Actually, Io should appear geologically soft. And then suddenly you see this staple mountain. A huge isolated peak, steep, massive, almost unnatural, 5 to 7 kilometers high, and it's not alone. Juno discovered several of these structures during its flybys in 2023 and 2024. Some of them are up to 18 kilometers high. For comparison, Mount Everest is 8 kilometers high. Olympus Mons on Mars is 22 kilometers high, but it's a shield volcano. And Io, as I said, no plate tectonics, no classic mountain ranges, no slow folding. So how do these monsters form? The answer is so counterintuitive that it almost sounds like science fiction. When a lava lake forms on Io, it often happens because the surface collapses, underground magma chambers. The roof collapses, a huge basin forms, but this mass doesn't just disappear. When material sinks in one place, it has to go somewhere else. And that's exactly what seems to be happening here. While a lava lake is being pushed down, the neighboring rock block is being pushed up. Not slowly, but abruptly. You can imagine it like a huge ball of modeling clay. You press in at one spot and it bulges out at another. Only it's not about dough here, but about rock kilometers thick. The result? Isolated, massive blocks shooting out from the surface. And as I said, completely without mountain ranges and without folds, but rather individual solitary peaks, like alien structures, and that's exactly what makes Io geologically unique. There's something else remarkable. Io has hardly any impact craters. And that's almost absurd in the outer solar system. Callisto is covered with craters, Ganymede as well, but Io, almost nothing. Why is that? Because its surface is constantly renewing itself. Volcanoes cover old structures, lava flows, sulfur snows, mountains collapse. It's like someone is constantly pressing the reset button. Geologically speaking, its surface is extremely young. And that means we're seeing processes there that are often hidden under billions of years of history elsewhere. Interestingly, that's hugging. It should be quiet.
Magnetfeld und innerer Aufbau. Io war eher
Ein Plan, it's ours.
Trotzdem gehören die Io-Bilder zu den spektakulärsten Aufnahmen der gesamten Mission.
Open bottles. Only a few words in the article of the long background don't have here. It's the most extreme landscape in the solar system. Black lava fields, sulfur snow landscapes, gigantic fault lines, and isolated mega mountains. And suddenly it became clear we have underestimated Io for decades. Now you probably want to know why no one is specifically flying there. This is where it gets strategically interesting. ESA's JUICE mission is on its way. It launched in 2023 on an Ariane 5 and is scheduled to arrive in 2031. The targets are Ganymede, Europa, and Callisto. NASA's Europa Clipper launched in 2024 on a Falcon Heavy and is expected to enter the Jupiter system in 2030. The target is Europa, but why not Io? We briefly mentioned this at the beginning. Quite simply, Io has no water. And without water, the priority drops. The search for life dominates planetary research. Europa has oceans beneath its massive ice shell, Enceladus has geysers, Titan has chemistry, and Io has lava. And lava is spectacular, but not as biorelevant as water, at least at first glance. There may be a flaw in this thinking. Io may not be hospitable to life, but it's an extreme laboratory for planetary energy. And it's exactly these extreme cases that help us answer bigger questions. How does gravity affect geology in the long term? Are moons in resonance systems? How much energy can tidal heating realistically provide, and what does that mean for exoplanets? Because tidal heating is not just a Jupiter phenomenon. It's probably one of the reasons why some exoplanets are warm enough even though they orbit far from their star. Io could help us understand alien worlds. Here's an aspect that's often underestimated. Io is electrically connected to Jupiter. Its movement through the gas giant's strong magnetic field induces a tremendous current. Io generates a kind of electrical flux tube, a magnetic connection between the moon and the planet. This interaction further feeds Jupiter's radiation belt. So Io is not just a passive moon, it is actively involved in Jupiter's energy system. It changes the magnetic field and influences the environment. With Juno, which is slowly running out of fuel, things could get very quiet around Io again. Europa is getting attention. Ganymede is getting attention. Mars, of course. Io isn't the focus. And that's ironic because Io is probably the most extreme geological laboratory we know. Space travel is changing right now. New heavy lift rockets, new mission architectures, and private deep space ambitions. With decreasing launch costs, priorities are also changing. In the past, every mission had to deliver maximum return. In the future, we might be able to afford to systematically explore extreme worlds as well. Io is not a candidate for colonization, but it is a candidate for understanding, and maybe for resources. Who knows? And anyone who wants to understand gravity, tides, and planetary energy can't ignore Io anyway. When we talk about Mars, about Europa, about Enceladus, it's always about life. Io reminds us of something else. Not everything in the universe is friendly. Not everything is hospitable to life. In fact, quite the opposite. But everything follows physics. And sometimes pure physics is more spectacular than any biosignature. Io is proof that gravity alone is enough to keep a world on fire. No star needed, no radioactive core decay as the main driver. Just resonance and patience over billions of years. And maybe that's the most important lesson. The solar system isn't just a collection of targets, it's a system of interactions. Io is an extreme case. And extreme cases are worth their weight in gold in science. Because they show us what's possible. If we understand how Io is driven by tidal heating, we also understand why Europa has liquid oceans, why Enceladus shoots out geysers, and why some exoplanets can exist, even though they're far from their star. Io is not a supporting actor, but the experiment that helps us understand the whole system. And maybe this is where the real irony lies. While we search for life on Europa and look for biosignatures on Mars, one of the most extreme geological processes is happening right next door and gets comparatively little attention. Not because it's unimportant, but because it doesn't promise an alien. But science isn't about wishful thinking. Sometimes the most important insight isn't there could be life, but rather this is how energy works in the universe. And Io is a textbook example of that. A moon that shows us gravity doesn't just determine orbits, but shapes entire worlds. Maybe in a few decades, we'll be flying regularly through the outer solar system, with large interplanetary spacecraft on missions that are no longer just searching for life, but for understanding systems. And then Io will no longer just be the strange sulfur moon, but what it truly is. Possibly the most brutal geological engine in our solar system. Until then, we have the images from Juno, Staple Mountain, Loki Patera, and sulfur snow under a black sky. A place where rock rises and falls like water. A moon that never stands still. My name is Serwan, and that was Mars Chronicles. Thank you for tuning in. Per aspera ad astra. Video rolling, audio rolling. Slate.